In this lecture, I'm going to talk about explanation of a mechanism that involves migration of bonds to make the most stable carbocation plus to make a ring. Typically, you get such a question in organic synthesis where it asks you to explain how the products are formed. Okay, now the first step to do an explanation for formation of these products, of course, is to follow Markovnikov's rule in your addition for your alkene, which states that the electrophile should end up on the carbon that is more substituted, which is this carbon, or the hydrogen should end up on the carbon of the double bond, which has more hydrogens. Okay, so if you forgot again and you want the official definition, just Google that word Markovnikov rule, you'll find it. So in this case, the hydrogen of HCl should end up where there's more, and you're only considering the part where when we're only considering the alkene that's participating in this first step reaction. So here, this carbon of the double bond of the alkene only has one hydrogen. This carbon has two of them, so this hydrogen should end up on the carbon that has more, which is this carbon right here. So that's what you're doing in the first step. So the double bond opens up by attacking the hydrogen, the chloride leaves, you end up with this structure. Now you have to define what type of carbocation you got. You have two carbons bonded directly to the carbon bearing the plus charge, so this is secondary. Plus you have a 4-membered ring which has ring strain. The smaller the ring, the more strained it's gonna be because of angle strain or ring strain. So we have to do a bond shift to see if we can make a 6-membered ring or a 5-membered ring from the 4-membered ring to make it more comfortable. And the reaction, and the molecule in the reaction mixture will just reason to do that, to make itself more comfortable. That helps to reduce the activation energy. So you're going to end up with this structure where this carbon here with a mark that I'm marking with an asterisk is this carbon right here after the ring opens up. Okay, so if it helps, just number your atoms, carbon atoms, you'll find that you're getting this, and this only comes by practice. Now you see this is a 5-membered ring, so it has, the 5-membered ring has less ring strain. It has less ring strain, and that's why you get bond shift here. And now the chloride that left on that step is going to come back. The chloride will come back to attack the carbocation carbon, and you get the first product, which is this product. Okay, now once you get this, you might have a rearrangement of some type moving to your right. So probably this ring will want to, because this is still secondary carbocation, so probably it will want to make itself tertiary. By moving this arrow, you're going to get, by moving this hydrogen with a bond on there, you're going to get a tertiary carbocation. Now if you don't know about hydride shifts and methyl shifts, please watch the video that I did. The link is posted in the description below this video. Watch the video on carbocations. It's going to give you a good refresher before you look at this synthesis, because this is more complex. Now once you get the tertiary carbocation, the chloride might choose to attack here to get that. Okay, here is another question. So suppose you are asked to explain the synthesis here to moving from here to here again, involving ring expansion during this reaction where you want to form an ether. Because this is an ether group. an oxygen between two carbons in presence of sulfuric acid and methanol. So the first step, as suggested, you're trying to form this acid and the conjugate base of the sulfuric acid. So to push the arrows again, use the lone pairs of the alcohol to grab the acidic proton on sulfuric acid that goes there. You get that conjugate base and the conjugate acid from the base. Now we can use this guy to continue the reaction with your starting material. So follow Markovnikov rule again. The hydrogen of the acid should end up on sp2 carbon of the alkene that has more hydrogen, which is this guy. So we start by pushing that arrow, neutralizing the plus charge. So you're going to get these two products. The plus charge will end up on the more substituted sp2 carbon of the starting material, and the hydrogen ends up where there's more hydrogens on the sp2 on the alkene, according to Markovnikov rule, as we did in the first example. And then this is a 4-membered ring. It's ring strained, it's not comfortable, so it needs to expand to make a 5-membered ring. So this carbon right here is this carbon bearing the plus charge, okay, and this carbon right here is this carbon right here. If it helps, again, you should number them. All right, now this is secondary benzylic, which can give another product, but the question is not interested in the other product, which I think is gonna be the major because it comes from the benzylic carbocation. We need to show how to make this one. All right, so probably you might want to do rearrangements. So this methanol will come back to attack, which is this methanol here that fell off from the first step, come to attack the plus charge. You end up with this product, and remember you have this conjugate base here. I'm going to write it again. Remember, you have this conjugate base here that was lost. Remember, you had this conjugate base here that was lost, which is this structure. It's going to be used as a base to steal the extra hydrogen and use that to neutralize the oxygen. That's how you get the final product, recycling your acid.